Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former Professor and Head of the Department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series intended for the BSc Honours Physics students. We have been going through a course of lectures on optics, and now we have been seeing the Michelson Interferometer, then visibility of fringes, coherence, temporal and spatial coherence, etc. And the contents of the lecture number 26 are as follows: formation of circular and localized fringes, white light fringes, visibility of fringes, coherence, wave train. And as far as the contents are concerned, they are interconnected, and in the lectures which we have seen earlier on Young's double slit experiment as well as the Michelson's interferometer, we have talked sufficiently about coherence. Unless you have got 2 coherent sources of light, you will not be having a stable interference pattern. I will ask a question: what do you understand by the words stable interference pattern? And secondly, we have seen the Michelson's interferometer, which has been used for several purposes. It has yielded good results with regard to the determination of velocity of light, determination of refractive index, estimation of thickness of a thin film, etc. It has got varied applications. In spite of all these things, when you go to the Young's double slit experiment as well as Michelson's interferometer, the term coherence plays a very important role. And again, the visibility of fringes. When will the fringes be visible or stable? As I told you just now, there should be 2 coherent sources. In the case of Young's double slit experiment, you make 2 slits. It is called a double slit. From a single source, you got a 2 slits, double slit. That gives rise to a stable interference pattern. By having 2 slits very close to each other, we will be having a stable interference fringes, or the fringes will be visible. I will ask the question: if the slits are kept far apart, instead of having the 2 slits closer to each other, if the slits are kept far apart, you have the source of light here, that is your S1, and S2 and S3 are the 2 light sources. Through 2 slits, they act as 2 coherent sources. They act as 2 coherent sources because light is coming from the same source S1, S2 and S3 will act as 2 coherent sources. Now my question is, if the 2 coherent sources are close to each other, what will happen? if the coherent sources are kept far away from each other, what will be the result? If they are kept closer to each other, then only you will be getting a stable interference pattern, or the pattern will be visible. If they are far apart, then there will be no phase coherence. It is called spatial incoherence. I will talk about spatial and temporal coherences in this lecture and the lectures to come. So, by spatial coherence, what I mean is, in order to get a stable interference pattern, in the case of Young's double slit experiment, there are two slits which act as two coherent sources. The two slits should be closer to each other. Then only there will be spatial coherence. Similarly, when you go to the Michelson interferometer, you have seen the interferometer earlier. Mirrors that you have got are M1 and M2. M1 is a stationary mirror, whereas M2 is a mobile mirror. The mirror M2 can be moved if the distances separating this point and M1 and this point and M2 are equal to one another, then you will be getting circular fringes. If they are unequal, what will happen? If they are unequal, there will be a time difference or there will be a phase difference. Because there is a time difference, they are called temporal coherence, or the two light sources will be incoherent from the point of view of time. So, it will lead to temporal incoherence. Therefore, in the field of physics, in optics, not only in optics, wherever you have electromagnetic waves, in electronics or in electrical engineering, in very many branches, the term coherence plays a very important role. And so, in today's lecture, I will be giving you the importance of coherence, and it is intimately related to visibility or formation of fringes. I told you just now, if the two slits are far apart in the Young's double slit experiment, it will lead to instability in the formation of fringes. The fringes will not be seen. So, there will be no visibility of fringes. I had the visibility of fringes in the contents. The fringes will become invisible, will become blurred. Similarly, when I talk of Michelson interferometer, what is the speciality about the first case? In the case of Young's double slit experiment, you come across spatial coherence. Here you come across what is called temporal coherence. By temporal coherence, what I mean is the time taken by the light ray to go from this point to M1 and M2, if they are equal, then you will be getting the bright and dark rings or bright and dark circular fringes. As I will be showing now, if the time difference is larger, then you should talk about temporal coherence or incoherence. So, I will now pass on to, before I discuss the visibility of fringes, obviously I am telling you the reasons why Michelson was made to think of the words coherence, then the division of coherence as temporal coherence and the spatial coherence and the visibility of fringes, formation of white light fringes. All these things came into the minds of Young. Young was the first person to talk about coherence. He was made to think of coherence. As I told you, you will have stable fringes. I told you the condition also. So, coherence is intimately related to both the Young's double slit and Michelson's interferometers. The circular fringes, as we have seen, and by now you should be having a very good idea as to how, under what condition you will be getting stable circular fringes in the case of Michelson's interferometer. The circular fringes are produced with monochromatic light when mirrors M1 and M2 are exactly perpendicular to each other. They should be perpendicular to each other. If we look into through the instrument T, that is the telescope, we can see the mirror M1 directly, as I told you in the last lectures, and you will be having a virtual image of M2 prime formed because of M1, and the light coming from the virtual image and the real mirror, they interfere and give rise to interference pattern, the circular fringes which are being formed, and you get circular fringes because you have an angle theta subtended by at the eye due to the two sources S1 and S2. S1 and S2 are the two sources, the virtual sources. Now, the distance between the two mirrors M1, M2 prime is D. The distance between these two will be 2D. All these things you have already seen, and they will lead to the formation of circular fringes. When will you get circular fringes? The two mirrors M1, M2 should be perpendicular to each other. What will happen if they are kept inclined? I told you in the last lecture, if they are kept slightly inclined, then you get what are called localized fringes. You get a wedge shaped film, you get a wedge. The angle theta is there between the two mirrors. Because a wedge is formed, you will be getting what are called a wedge shaped film, or they call localized fringes. When two mirrors are tilted, they are not exactly perpendicular to each other, and therefore the mirror M1 and the virtual image M2 prime are not parallel to each other as we had in the earlier case. In this case, the air path between them is wedge shaped, and the fringes formed will be appearing straight. If one of the mirrors is moved, the fringes will move across the field of view. The position of any particular bright fringe is taken up by the one next to it. White light fringes. Now, so far we have been talking about the formation of circular and air wedge, the straight line fringes, using a monochromatic light. Instead of using a monochromatic light, if a white light source is used, a few colored fringes with a central dark fringe can be observed. In observing these fringes, the mirrors are slightly tilted as we did for the localized fringes, wherein the position of M1 is found to be intersecting the mirror M2 prime. This position is often difficult to find with white light. The position can be best located with monochromatic light. When the fringes come straight, then a very slow motion of M1 in this region using white light will bring these fringes into the field of view, when a central dark fringe is surrounded by about 8 to 10 colored fringes on either side. These fringes are useful for the determination of zero path difference. Because we saw the path difference, you wrote in the earlier discussion we had with respect to Michelson's interferometer, we had 2D cos theta plus lambda by 2 and so on. We had a path difference due to dissimilar reflection, etc. That is the reason why I am talking about zero path difference here. Visibility of fringes. What do you mean by the terms visibility of fringes? By now you should be knowing what I would like to impress upon you, what I would like to make you to understand by visibility of fringes. The fringes that you get on the screen or you observe through a telescope, in the case of Young's double slit experiment, will be distorted, will not be clear if the two slits are kept far apart. I told you using diagrams in the earlier lectures. In Tel Aviv, in Israel, in Tel Aviv, in the capital, we talked about break spots, that is the break walls, that is when water wave is coming, passing through to break walls. By break wall, what I mean is there is opening here, there is ocean here, the sea wave is the wave coming, the mechanical wave coming on the surface of water, then there is a break wall, there is opening here, opening here. If the two openings are separated by a very large distance, then you will be getting, you will have, you have a plane wave front. On the other hand, if the openings are closer to each other only, then the waves coming from the two openings will be interfering. So, in order that interference occurs, the openings should be closer to each other, otherwise there will be no stable fringes. Let us have a break and come back after the break. Welcome back after the break. The important concepts of visibility of fringes and coherence. Coherence will be divided into two cases, namely temporal coherence and spatial coherence. I told you just now, in the case of Young's double slit experiment, it is the spatial coherence which is of importance. In the case of Michelson's interferometer, it is a temporal coherence. I will come to those cases later, but in both cases, the fringes will be stable or visible only under the conditions which I told you earlier. By visibility of fringes, what I mean is the fringes should be stable. You should have a stable interference pattern. In the case of Michelson's interferometer, the intensity I is given as 4 times A square into cos square delta by 2. What is A? A is the amplitude and delta is the phase difference. And the phase difference delta is given as 2 pi by lambda, where lambda is the wavelength of the monochromatic source, into 2d into cos theta. What is your d? D is the distance which separates the mirrors M1 and M2 prime, which I showed earlier in the picture. The intensity is maximum, obviously, when delta is an integral multiple of 2 pi. The intensity is 0, obviously, on the other hand, the intensity is 0 when delta is an odd multiple of pi. A phase difference of pi corresponds to how much? A path difference of lambda by 2. A path difference of lambda by 2 will lead to constructive interference and the intensity obviously will become 0. When a monochromatic source of light is used, the minimum intensity of fringes is 0. The visibility of fringes in the case of a Michelson's interferometer is defined as visibility V is equal to I max minus I min. Max and min correspond to maximum and minimum intensities, that divided by I max plus I min. For monochromatic light, as given earlier, I min is equal to 0 and therefore V will be equal to 1. However, if the source of light is not strictly monochromatic but contains two nearby wavelengths, the condition for maximum intensity for both the wavelengths is satisfied only for particular values of path difference 2d cos theta. 2d cos theta is the path difference, the delta is the phase difference. Phase difference of 2 pi will correspond to a path difference of lambda, all these things you know. Therefore, the condition for maximum intensity for both the wavelengths is satisfied only for particular values of path difference 2d cos theta. As the value of d is altered, the two wavelengths do coincide over a considerable range, and here the fringe visibility is a maximum. For values of d other than the maximum intensity positions for both wavelengths, the two fringe patterns will be complementary provided the intensities from both the wavelengths are equal. If intensities are not equal, the minimum visibility will not be 0. So, the intensity will be neither be maximum nor will be 0. The minimum visibility will be given by an expression of this kind, A1 square minus A2 square by A1 square plus A2 square. That gives them minimum visibility, where A1 and A2 are the amplitudes. Hence, the source will be perfectly monochromatic if visibility is maximum and constant for different values of 2D cos theta. If the visibility changes with the change of 2D cos theta, the source is not strictly monochromatic. Now, we pass on to a very important section, namely coherence. What do you mean by coherence of light? You have a source. I am in a room where I have got a lot of light sources. Light is coming from here, from different mercury vapor lamps. On the other hand, instead of having mercury vapor lamp, suppose I have got a sodium vapor lamp. You know, sodium vapor lamp is a white light. Sodium vapor lamp is a monochromatic source. Now, what do you mean by monochromatic source? When we talked about Michelson Interferometer, we talked about cadmium red line that was taken as a monochromatic source. Now, in the case of sodium vapor lamp, you have two lines, D1 and D2. One line is having a wavelength 5890 angstrom unit, the other is having a wavelength 5896 angstrom unit, and for all practical purposes, you consider a sodium vapor lamp as a monochromatic source of wavelength 5893 with the average of 5890 and 5896. Even if you take a cadmium line, or later people felt instead of cadmium red line, which is taken as a monochromatic source, or which is treated as a monochromatic line by Michelson, the later researchers found a particular line from mercury vapor lamp to be more monochromatic. What do you mean by more monochromatic? There is nothing like ideal monochromatic. There is no source which can be called an ideal monochromatic source. What I mean by this is, you have some line here. It may be 5461 angstroms, the green line coming from mercury vapor lamp. It cannot be called as a monochromatic light because there be a wavelength spread. If you carefully see through a powerful spectrometer or spectrophotometer, it is not a single line, it consists of multiple lines. Therefore, no source can be called as an ideal monochromatic source. Every source will have a bandwidth. You got a bandwidth, you got a width. The wavelength will not be strictly, will not be having a particular line. There will be a line broadening, there will be a bandwidth. I will be showing the bandwidth and the connection between the bandwidth and the coherence length and so many other things in the lectures to come. The point is, there is no source in the universe which can be called as a strictly monochromatic source because of various reasons. I am going through various reasons here. We have so far assumed tacitly that light sources emit perfect harmonic waves. If they are harmonic waves, then you should have got interference pattern. On the screen, you will be having interference pattern. If you have got two sources, right, two independent sources, you need not have biprism, you need not have double slit. You have two monochromatic sources. The two light coming from the two sources will be phase incoherent. That is the reason why you make two slits and so on, or you make use of biprism. In an ideal harmonic wave, there exists a definite relationship between the phase of the wave at a given time and at a certain time later, and also at a given point and at a certain distance away. What do you mean by at a given point and a certain distance away? That is what is called spatial coherence, right? Then earlier I state a definite relationship between the phase of a wave at a given time and a certain time later. That is a temporal coherence. I talk of time. later I talk of space, two slits separated by some distance in Young's double slit experiment. That is a spatial coherence. In the case of Michelson Interferometer, the light coming from the two mirrors M1, M2, there is a time difference that will lead to a temporal incoherence. In reality, light sources do not emit perfect harmonic waves. Even the very best practical monochromatic source emits a finite range of wavelengths, and the light waves are quasi-monochromatic. There is nothing which can be called perfect monochromatic source. It has a bundle of rays, bundle of lines. If it were not so, supposing the light coming from a very monochromatic source is strictly monochromatic, then you should have had interference pattern. Light waves would have been ideally incoherent and interference would be observed at all times. In practice, light is emitted from a light source when excited atoms fall from upper excited state to a lower energy state. The atom gives up energy in the form of a photon. All of you know this transition takes a time of 10 to the power of minus 8 seconds. It means that atom starts emitting a light wave, then it keeps on sending waves for a period of 10 to the power of minus 8 seconds. You get wave train. You get number of waves in a period of time 10 to the minus 8 seconds. That is the lifetime of the atom, of the electron to stay in a particular energy level. Therefore, an emission event produces a light burst. I will show the light burst. This is a light burst. A bunch of waves coming is called a wave train. It has a length L. What do you find in length L? In the length L, you got almost harmonic waves, right? Your harmonic. And after that, you will be getting another atom will be coming down from same source. It will be coming, the atom is coming from excited state to the normal state, or the electron is jumping from the higher state to the lower state. Another wave train will be coming. When another wave train is coming, then you will be having what is called a phase break, because there will be a phase difference between this wave train and another wave train I will be getting after a time delay of 10 to the power minus 8 seconds. So, each light burst occurs over a period of 10 to the power minus 8 seconds only, during which period a train of finite wavelength having a certain limited number of wave oscillations is generated. What do you mean by limited oscillations? You can count the number of oscillations. You got the number of oscillations, this is called the coherence. This will be calling as a coherence length later, but the point is you have number of oscillations in this finite length, that is a wave train. Such a light burst is known as a wave train or a wave packet. So many wave trains will be coming out from a light source in a short period of time. At some time, the atom again receives energy, it jumps to excited state, and subsequently another burst, the atom will be coming down, another wave train will be coming. So, between this wave train and the earlier wave train, there will be a phase difference. The emission events occur quite randomly, and that is what you have ordinary light source. If the events occur simultaneously, that is a laser. You know, that is the stimulated emission of radiation. So, here the events are taking independently. Each atom in the source acts independently, and different atoms emit wave trains at different instants, and their combination in millions and millions constitute the light coming from a light source. In order to appreciate some of the peculiarities of natural light, the following fact is to be well understood. So, and we will now try to summarize what we saw in today's lecture. The summary goes as follows. Formation of fringes in Young's double slit and Michelson interferometer lead to the detailed study of visibility of fringes, white light fringes, and coherence. The fact that light in general emitted by a monochromatic source is not coherent and there is no source which can be called as an ideal monochromatic source. We will now pass on to the question session. Here are the questions. Question number 1. When do you get stationary fringe pattern in Young's double slit experiment and Michelson's interferometer? Why do fringes become invisible? How do you define visibility of fringes? Question number 4. How are white light fringes obtained? With this, we come to the end of lecture number 26. In the lectures to come, we will deal with coherence at a greater depth. Thank you.